Hi, it's Paul Bamberg. 2 years ago, I made a mess of Proof 9.2 in the first lecture for week 9, and I corrected it in the second lecture, but it doesn't appear to have shown up nicely in the posted videos, so I decided I'd just do it over again from scratch. This is a very nice proof because it's a mixture of algebra and analysis. What we're trying to prove is the infinite triangle inequality. We proved the triangle inequality for 2 vectors several weeks ago. That was just a matter of algebra. We can prove the triangle inequality for m vectors by induction, but we need some slightly fussy real analysis in order to prove that the result continues to hold for an infinite sum. In other words, if you know that you have an infinite sequence of vectors whose lengths form a convergent series, you want to show that the length of the sum of all those vectors is less than the sum of the lengths. So, the first thing we have to show is that the quantity on the left-hand side exists, that the length of the infinite sum of vectors exists, and in order to do that, we're going to show that the sum of vectors itself is a convergent series. Let's look at the jth component of the ith vector. The magnitude of that jth component, of course, is the square root of its square. To that square, we can add the square of each of the other components of the ith vector. That's certainly going to make the results bigger, and that square root is what we mean by the length of the vector a sub I. So we've now shown that the magnitude of the jth component is less than or equal to the length of the vector. If we add together these quantities for I going from 1 to infinity, then the comparison test for infinite series says that the sum of the absolute values of the jth components of the vectors is less than or equal to the sum of the lengths of the vectors. Unfortunately, that's not quite what we want. We don't want that absolute value, so we invoke theorem 0.5.8 in Hubbard that says if a series is absolutely convergent, that is, if the series of absolute values converges, then the original series without the absolute values converges, and we can conclude that the jth components of these vectors form a convergent series for each component. Fortunately, we've also proved, this was seminar topic 4, that a sequence of vectors in Rn converges if and only if it converges component-wise. We know that the infinite series of components is convergent for each component j. It follows that the series of vectors is convergent. That converges to some vector, and since that's a well-defined finite vector, its length is well-defined. That takes care of the left-hand side of the equation. Now let's do a bit of induction to prove the triangle inequality for m vectors. Sorry, I should have written an m there, but I'm not going to fix it and start over. This is a straightforward inductive proof. We go back to week 2, it is, I think, where we proved the triangle inequality from the Cauchy-Schwarz inequality, that the length of the sum a1 plus a2 is less than or equal to the sum of the lengths. Now let's do the inductive step. We'll assume that this is true when the upper limit m has some value k, and we want to prove that it's also true when the upper limit of summation is k plus 1. How do we do that? We say the sum of k plus 1 vectors is actually the sum of 2 terms, the first being the sum of k vectors, and the second being the k plus first vector. And by the triangle inequality for 2 vectors, that's less than or equal to the length of the sum of the first k vectors plus the length of the k plus first vector. But now we can use our inductive hypothesis. We can assume that the triangle inequality holds for the sum of k vectors. In other words, the length of the sum is less than or equal to the sum of the lengths, and therefore the sum of the first k plus 1 vectors has an absolute value that's less than or equal to the sum of the lengths of the first k vectors plus the length of the k plus first vector. This, of course, is just the sum of the first k plus 1 vectors, and we've established the truth of the triangle inequality for k plus 1 vectors based on the assumption that it's true for k. We've got a base case, we've got an inductive step, and so we have proved this for all m greater than or equal to 2. Now we're almost done. We have to let m approach infinity, and this is a little bit tricky. What you want to do is first let m approach infinity on the right, and then let it approach infinity on the left. You can't just cavalierly replace m by infinity on both sides. What's nice about the right-hand side is that it's a sum of non-negative terms. That means that the partial sums, there's a partial sum for each m, form an increasing sequence, and since it's an increasing sequence, each of the partial sums is less than or equal to the sum from 1 to infinity. We're given as a hypothesis that this sum from 1 to infinity exists. Why is that useful? Well, we've got a bit of a problem on the left-hand side. There's no reason to expect that the sequence of partial sums on the left, well, it's not really a partial sequence of partial sums. It's a sequence of lengths of partial sums. It could be, for example, that a sub 1 is a very large vector directed to the right, and then we're adding on a lot of vectors directed to the left, making the length get smaller and smaller until we finally reach a limit. So we can't say that this is an increasing sequence, but we know it's well defined. In step 1, we proved that the sum of all the vectors from 1 to infinity had a limit. Its length is well defined. We also have an upper bound that holds for this quantity for each value of m, and therefore that same bound must hold for the limit of this sequence of real numbers as m approaches infinity, and that's the result that we need. We've now shown that the length of the sum of all the vectors from 1 to infinity is also bounded by the sum of the lengths from 1 to infinity, and that's the infinite triangle inequality. If you master this proof, you've really got most of real analysis and a substantial amount of algebra under control.